Let's start with just the basic idea of continuity. This is continuous. This is continuous. This is not continuous. So if you have a whole, you're not continuous. If you have a piecewise function, you are not continuous. That makes a jump like this. Okay? So the idea of continuous means that at that given point, there is the value at that point, but also the limit approaches that. This is at the heart of continuous. One, that the function has a value at A. In other words, that actually exists. So when you plug it in, the function has to give you a value for that. Two, that the limit also exists. So both of them must exist. And that they would be equal. Now, why does that make sense? Well, so let's say the limit exists. So let's say it looks like this. This limit exists at this moment in time because from the right and from the left, we meet that. So yes, it exists. But if it's actually continuous, what that would also mean is that at that given value for A, then it would fill in that hole because we know that the function has that same value. So that makes sense, doesn't it? Continuous would mean it came along and the limit brought me there, and the limit took me away from there. So it came in from the left and the right, but it also is there. Therefore, it is continuous through the process. So this little guy right here is the heart of the argument that we're in, and you're going to see me hit that note many times. All right, so here were the instructions of this. It says, use the three-part definition, 3 parts of continuity to determine if the function is continuous at the value of A. So 3 steps to obtain if it is or isn't continuous. Second, if it is not continuous, tell me whether it's removable or non-removable. So that has to take place in each of these questions. Step 1. Does the function exist at the value? So in it goes. And we get the value of 5. So step 1 has established that indeed we do have a real value that comes out from this, so it does exist. Step number 2 is to evaluate the limit as x approaches 3 of that function. Okay, this is what we want to evaluate. So that, of course, is the limit of 2x minus 1 as x approaches 3. Now, one thing that you're being instructed is, as you write these things, you keep the limit notation there, but as soon as you substitute in, which we're about to, now you can just simply say 2 times 3 minus 1 equals 5. Now here is the heart of what it means to be continuous. You have established that the value at the moment is 5, and the limit at that same moment is 5. So therefore, you can now say, therefore, f of x, that function, is continuous at x equals 3, and we are there. Why is that true? Because f of 3, that value, equaled the limit as x approached 3 of that function. Please take note of many things here again, right? 1, we found the actual value, step 1. We found the limit's value, step 2. We decided that they were actually indeed equal. Therefore, it is a continuous function, and it's continuous at a given moment in time. One question you might ask is, why did I only do it at the general limit and not from the left and the right? Well, in this case, our function had no restriction to it. There was no denominator that became 0. There was nothing that needed to be simplified. There was, it's just simply a function that I could evaluate based off of direct substitution. So I did that. You could have evaluated it from the left and the right and then declared the general limit, but in this case, we're okay with just the general limit. All right, we now have a piecewise function, and they handle themselves a little bit differently. First thing I did is evaluate to see if the function does exist at 1. When x is 1, the value is 5. And so our first of the 3 steps have been taken care of. Step number 2 is to evaluate the limit. Now, in this case, I have 2 pieces, and they both need to be evaluated. A left side piece and a right side piece. I didn't have to do that in the last example, but this is a piecewise, and they come in pieces. Now, a couple things as Ms. Taylor informs me of. One, that when you're doing a piecewise function, f of x isn't good enough here. You're going to want to put the actual piece that you're evaluating. For the values where we are less than 1, that is our group up here, right here, when we're less than 1, this is our function. When we're greater than 1, or on the high side of it, this is our function. Now we're going to evaluate by putting it in. So now you put in your value there, and we get the value of a 5. Here, you'll put in your 1, add it to 4, and you get your value of 5. So you've evaluated it from the left and from the right, and so actually, let's summarize that. That means that the limit as x approaches 1, the general limit, of that function does equal 5. So do you see I'm able to make the statement now of the general limit of the function because I tested it from the left and from the right. We both got 5, so that limit then does equal 5. Now, that is important to you and I. Why? Because this, the value at the moment, is equal to the limit at the moment. And so we can make the final statement to say, therefore, f of x, that function, is continuous at x equals 1. And again, basically, our answer is, and I'll run up here to do it, because f of 1, the value at the moment, is equal to the limit at that same moment. That is exactly why it's continuous. This is the heart of the definition of it being continuous. All right, I've started this one for us, a piecewise as well. First thing, what is our value at that moment? It is 2, and it exists, key moment. Next, we're dealing with a piecewise function, so we need to test out the lower value coming from underneath and the value from above. Notice 2 things happened here. One of them is from the low side, and one of them is from the high side of 2. And when we solved those, the good news is we got 1, and we got 1, and so the general limit does exist, and our value is 1 as we approach 2. Now, the conflict of interest at this stage is that we got an answer for the limit of 1, but the value is there. Ultimately, think about it this way. We came on in and we limited out at like the 1 value, but the actual value is up here at 2. This is what we're seeing. So our conclusion is that it is not continuous because, well, actually exactly by the definition, because the value, that's supposed to be g of 2 doesn't equal the limit as x approaches 2 of g of x. It does not do that, right? Because on this side we have a 2 value, on this side we have a 1 value, and in other words, the limit comes in, but we are up here. And this is known as a that point got removable discontinuity at x equals 2. So this is our statement. It was not continuous because the value of the limit did not equal the value at the moment. That's known as a removable discontinuity at the x equals 2 value. So the next question, many of you somehow solved and got different answers here than I'm getting. So First of all, you don't do any simplifying or anything to this. You just find out, does the value at h of 1 actually exist? And when you put that into our equation, you're going to find out that it actually doesn't exist, does it? That this value here zeroes out, this value here zeroes out, and we know that to be a whole. But ultimately, what that means is that value does not exist. Immediately, we now know that this is not continuous. We know that immediately because there is a hole in our graph. So now all we have to do is determine the type of discontinuity. And now let's look at the limit. Let's talk about a few of the things that I saw as I graded. First of all, when you make a statement like this, again, good notation. The limit as x approaches 1, here is the original one. Now notice that is a limit statement. I'm going to write that again as I simplify that limit. So I was able to factor and simplify, and now I'm down to here. Now I can evaluate this for 1. Back here, it gave me that indeterminate form. But by simplifying this as a part of my limit, now I just basically sub in a 1, and a 1 plus 1 is a 2. So I am able to determine that limit actually does exist. It does actually happen. So that helps me to know what I've got. I have a limit that comes into a value at 2. It actually exists. But I have a whole or a value that is not at that moment in time. This is, we are not continuous at x equals 1, and it is a removable discontinuity. Why? Because h of 1 did not exist, right? Does not exist, but the limit did. So we know that we actually have a value, an actual limit that came into that location, so that's how we know it's removable, but we know that there was a hole at that given moment in time. In the last two questions, we changed what we're attempting to do here. We're now trying to make it continuous. And ultimately, what both of these questions should start with is if it's continuous, then the function at a should actually equal the limit as x approaches a. This is actually, the beginning place. So this is something we would look for in your work, is that you're saying, okay, I'm trying to make this happen. Now, the function at a, of course, is 8. And so this side we will have as an 8. On the other side, we will do the limit as x squared minus a squared over x minus a as x approaches a. Now, to evaluate a limit, you would plug in the a, but we have a problem. If you plug in a, you get 0 over 0, which is that indeterminate form. So again, we would go through the simplifying process. Notice I'm still carrying the language of the limit with me. X minus a, x plus a, over here is x minus a. You know where this is going. You see how this simplifies. Now we are getting closer to being able to talk about, the value that would make this work. Now remember, we are trying to solve this or determine what a variable value would make this side equal to this side, which is 8. So we need to assess by plugging that in. And that's the evaluating part. When you plug that in, you get 8 equals 2a. And a then equals 4. So again, the assessment part of this, or the evaluation as x approaches a, is to plug in a, and you get just 2a. That's what it comes to. But that is very easy. 2a has to equal 8. The key, my friends, the key is that you began with the statement about continuity, that this is the heart of what it means to be continuous right here. Now, this is something you give in homework and not on a test, just because there's a lot of moving parts here. But first of all, if you're going to make a piecewise function continuous, then you have to make the pieces connect to each other. So, in other words, the idea is if a piecewise function, it comes in, and then it connects with another piece, and then it connects with another piece. That's how you make it continuous. So what you and I are trying to do is find the values so that at the connecting points, you do have a continuous function. So that's why we're doing two different things. We're going to set up kind of for the values dealing with 4 and solve between these two. And we're going to do it again between the 5 because we need to connect these two together as well. So let's show you the work I'm going to do. To be continuous in a piecewise, you have to always evaluate the left piece and the right piece, and they have to be equal. That's the whole idea of being continuous, is that the left limit equals the right limit. So the limit does exist, right? It's continuous. So I say the limit as x approaches 4 from the negative side is x of x squared equals the limit as x approaches 4 on the positive side of ax plus b. Now let's evaluate. When you plug in a 4, you get 16. When you plug in a 4 for the x value, you get 4a plus b. Let's work on the other intersection, this intersection here between them. And so we get the limit as x approaches 5 from the negative side, that would be the low side, which is ax plus b, equals the limit as x approaches 5 from the high side of the square root of x plus 31. Now we evaluate. In goes the 5, I get 5a plus b. In goes the 5, I get the square root of 36 as this. It's at this moment that we do a little bit of that whole business of a system of equations to finish the equation off. And, hold on a second, that's a 6. 5a plus b. I'm going to do subtraction as my method here, so I get 10 equals negative 1a, and the b's cancel, and a equals negative 10. When you plug that value into one of these, you're going to get b equals 56, and those would be the two values that basically create the perfect connections between these two pieces and these two pieces to continue continuity. What I would say is we did not see these kinds of statements, the limits taking place to obtaining the equations and then the solution. Good luck, friends.